At the beginning of this quarter, I saw a news article that said, that mentioned that there was a new publication that was starting for Southern California called citric acid. And I was excited about that because that's an organic molecule. You can buy that at Sprouts Market, grocery store, or other pure, absolutely pure crystalline citric acid. It's like one of those kinds of exciting molecules you can buy in pure form. But when I looked at the publication, I went to the website. It actually had nothing to do with chemistry or the structure of citric acid. It took me a while to figure this out. Apparently, this is a magazine that's related to literary arts, a quarterly of imagination and reimagination. And the citric acid was a reference to the fact that this is Orange County. And oranges, citric acid, I think somebody was trying to make an interesting play on that. And I think the founding editor of this is somebody from UCI. I don't know enough of the departments elsewhere, but I wanted to go ahead and talk about citric acid. Why is that an exciting molecule to anybody? Why would anybody be interested in citric acid? How many of you have taken Bio 98 here at UCI? Some of you. I don't know if you had to memorize this cycle called the citric acid cycle. I had to memorize that. What a ripoff. I've been waiting 30 years to use this, never had any reason to look at it again. And it's sad because there's a lot of interesting organic chemistry in here. And when you look at the source of diseases and problems that we have, cancer, diabetes, Alzheimer's disease, inflammatory diseases, this is not the source of any of those problems. You've never heard anybody say, oh, my back is so sore, that darn citric acid cycle is really getting me. That doesn't happen. So it's just this archaic thing that they force and maybe will continue to force students to learn that isn't really relevant to modern medicine or the kinds of things that are important, that I feel like are important for biology and biochemistry. But when I look at this citric acid cycle, there's just a bunch of organic transformations in here. So there's some really fascinating chemistry that goes on right here. And you can see they're referring to something called a Claisen condensation. That's coming up. Maybe we'll get to that in this lecture, certainly by the next lecture that we have. There's addition of water or loss of water from a double bond. Right? This is an E1CB elimination mechanism, and we know about the E1CB type mechanisms. We know about conjugate addition reactions, 1,4 addition reactions to add nucleophiles into enones. This kind of chemistry that you see over here is a little bit more complex than we're ready to talk about right now. But there's a lot of chemistry here that seems pretty standard, like ester hydrolysis. I'll just write that here. We know how to handle that now. Hydride reductions, you know about sodium borohydride reductions of carbonyls. And again, there's some other chemistry here that's a little bit different. That's an oxidation reaction, and we've discussed mechanisms of oxidation reactions. There's another oxidation reaction up here that you could do right with PCC if you wanted to. I mean, the enzymes do this a different way. But all of these involve arrow pushing mechanisms that you could write out on a piece of paper if you wanted to. If you wrote down the structure, you could write out arrow pushing mechanisms. But unfortunately, none of these are any more interesting than any of the other zillion catabolic or anabolic pathways, biochemical pathways that you have inside the cell. I'd say arguably these are completely not worth your time to have memorized, except because they might put it on an MCAT or some DAT or standardized exam. So I'm sorry if you had to memorize that like me. Again, I'm still waiting to figure out when that's going to be useful to me. But let's talk about what's exciting. Sorry, let me come back to this cycle. This cycle tells you that you can start off with citrate, that's the anion of citric acid, and then it gets converted to a bunch of other stuff and then re-arrives here at citrate. But it never discusses about where does that citrate come from? How does the citrate get into this cycle? Somewhere else in the cell, in some other cycle or some other anabolic process, there must be a biosynthesis of citrate. And let's talk about that chemical reaction that generates citrate. Citrate is generated from an aldol reaction. And let's take a look. Aldol reactions, that's exactly what we're talking about in this quarter. And the two pieces that are used to make citrate are acetyl-CoA and oxaloacetate in this aldol reaction. There is an enzyme that does two things. So if we take a look at the starting material here, you can see that you're going to have to do some sort of an aldol and make a carbon-carbon bond. And that's what this enzyme is catalyzing. And the enzyme also catalyzes a bonus reaction, which is the hydrolysis of this ester bond. And in this case, it's a thiol ester, but it's the same idea as any oxygen-based ester. There's no difference. There's a hydroxy group in the active site, hydroxide anion. And so this enzyme is simply is creating an enolate, or the equivalent of an enolate, and then that's adding in to make an exciting new carbon-carbon bond. And that's what generates, it doesn't generate citric acid. In fact, there's no citric acid floating, or not any appreciable amounts of citric acid floating in your body. Because when you put these types of groups, which have a pK around 5, into a buffered solution like cells, the inside of cells, the serum in your blood has pHs between 7.3 to 7.5. And the Henderson-Hasselbalch equation will tell you that almost all of those exist in the anionic forms. At physiological pH. So there's no citric acid in your body, it's citrate anion, the trianion that's floating around in your body. We have an exam coming up on Monday, and you've got to study like crazy, practicing every problem you can get your hands on to be ready for that exam. I just finished writing the exam, and I made every attempt to write questions that you hadn't seen before, because I'm trying to assess, what is your problem-solving ability with problems you haven't seen before. When you go out and you study the citric acid cycle or any other chemical reaction that involves organic molecules, you're going to be trying to assess things, questions, molecules that you haven't really thought about before. So you need to apply our tools to molecules you haven't seen, or to transformations you haven't seen. So work as many problems as you can. We're trying to have extra study hall hours this week. Please take advantage of those. I have normally hold mine on Friday. I'm still going to be there Friday at 9 a.m., even though it's a university holiday. But I also have a special office hour listed, study hall listed for tomorrow morning. And please attend, because you don't have to have any questions. Just show up and study. And if you have a question, you can ask it. I'm doing them by Zoom. So you're going to study anyways. Why not study while somebody's there to answer your questions for you? Okay, as I mentioned, oh yes, there is a strike that is currently planned for next week. There could be a strike that starts on Monday if they can't do something with the negotiations. So that doesn't affect us. We are still going to be taking an exam in this class on Monday morning, but it could mean that we'll be slower to grade those exams or process those in another way. So please be patient if there is a strike with our instructional team and with your other courses that you're taking. Now, I apologize for that fiasco that we had in lecture when my iPad pencil was not working. But we were able to get to this stage where we were talking about aldol condensations. Aldol refers to aldehyde, but you can also do, as we mentioned, aldol reactions using ketones. They're not as good. That's not as common of a recipe, sodium hydroxide, to do aldol reactions with ketones, but it's possible. And in this case, I would write heat here just to be clear that there's going to be an elimination. Otherwise, that wouldn't be a spontaneous elimination. Now, you've got to practice the aldol reaction. It is present in so many different ways. Citric acid, biosynthesis of terpenes, isopentenyl pyrophosphate, which leads to all of the steroids, hyperlipidemia, and heart disease. And if you don't practice that reaction, you're not going to be able to see it when it's right in front of your face. And so I expect you to practice the aldol reaction and the aldol condensation so much that you're able to recognize exactly what was the starting materials for an aldol reaction. I expect you to look at this molecule and instantaneously recognize aldol. That was an aldol reaction, right? And the two pieces that you would generate here would look like this. You just stir this with sodium hydroxide and heat. They use that industrially to prepare a fungicide that they put in barbershop comb spray or whatever they put on there. So you know, what's not so obvious to you if you haven't practiced this is it requires two molecules, and you always have two molecules. I don't have to write the second molecule here, but let me just remind you, of course there's more than one molecule in solution. And I expect you to know that yes, these have alpha hydrogens here that could be deprotonated and form enolates and undergo aldol condensations if you're heating that in the presence of base. And if you have not practiced that, you might not know what the two carbonyl components should look like. Again, when I come down here to the second problem, instantaneously you need to recognize that that came from an aldol reaction. And you have to be able to draw out the starting materials here. So if I draw out these starting materials, let me teach you a little trick here that's, you know, it may be kind of difficult for you to see what came from what initially, but I'm going to go ahead and draw out what I think is the starting material for this, right? I have to have something that can form an enolate, and I was going to write a pH here, but let me go ahead and draw out this whole ring. Now, how do I know that this looks good, that I didn't make a mistake? When you're taking an exam of some kind, you want to make sure you didn't make a mistake in the structure because you're going to lose points for not being careful. And usually when we're trying to figure out an arrow pushing mechanism or you're trying to work through a retrosynthetic problem, I encourage you to use the concept of atom mapping to see how do the atoms or atom groups in the starting material relate to the atom groups in the product. And what you look for is, for atom mapping, you look for CH groups. So CHs, I'll write CHs, not the H bond. But in other words, when I come over here, I can see there's a carbon over here that has no H's. It's next to a benzene ring. So if I had to guess in the starting material which carbon was next to a benzene ring and had no H's, I would say this is a pretty good guess, right? That would map. That looks like a good mapping. And next to the carbon number 1 that has no H's, I see a CH2 group right next to carbon 1. Well, there's a CH2 group right next to carbon 1. That looks like it. Let's call that 2. And you could use any symbols you want. You could use alpha, beta, Mickey Mouse, emoji characters. Just numbering is convenient to use. You could use mixtures of numbers and letters if you want. Doesn't matter. I see over here next to CH2 group number 2, I see another CH2 group. And so it's kind of good that when I look at my guess structure here, I'm guessing at this. Okay, that's good because I have a CH2 group number 3 next to CH2 group number 2. And over here, when I look at the product again, I can see that there's a carbon that has no H's. It's a carbonyl carbon. And fortunately, I can see that there's a carbonyl carbon, so I'll call that 4, over here in my proposed starting material that maps right onto that, a carbon with no H's. Now I get to the last carbon atom here, number 5, that has a CH, and I'm down to the last carbon. So really, you can see there's a difference here. In the product, this carbon number 5 is a CH, and over here in my proposed starting material, it's a CH3. If that was a correct guess somewhere in the arrow pushing mechanism, I'm going to have to deprotonate that twice. I'm not asking for the arrow pushing mechanism here, but if you were doing an arrow pushing mechanism, you now know you have to do 2 deprotonations, right? Not all in one step, but you need to have steps in your mechanism that involve removing a proton and then later removing another proton. So atom mapping can help you. It's a way to try to check relationships between starting materials and products, whether it's a multi-step synthesis or a multi-step mechanism. Try to use that concept of atom mapping. Let me finish writing the word mapping here. Whoops, right, atom mapping. I'll just say atom map. Atom map CHs. It's a way, and the structures will start to look confusing with aldol reactions. When we come down to this bottom case, this is just an aldol addition reaction. There's no condensation part to this, but I hope of all those bonds there, you instantly see that that's the bond. And you'll have to practice this. I've practiced it a bunch. You have to practice it to see which of those bonds was formed through an aldol reaction. Right? I can clearly see that involved taking 2 carbonyl compounds, 2 aldol pieces, and one of these forms an enolate and attacks another one. And notice how sometimes the ethyl groups are bent around in different orientations. You don't have to write two copies of the same molecule because there's 10 to the 23rd molecules in there. You just have to write 1 copy. So again, over here, if we just wrote sodium hydroxide in this second reaction, that's sufficient because I told you that in cases where you would have this kind of conjugation in the product, you don't need to add heat. So the heat in this case is optional. I'll go ahead and write it there in parentheses. Whether you added heat or not, you would get that condensation, the elimination product with the alkene. Down below, you don't want it to eliminate to generate that product. Right, this would be something involving just sodium hydroxide. Could you use sodium methoxide? Yes. Could you use sodium ethoxide? Yes. Could you use sodium T-butoxide? Yes. But, you know, sodium hydroxide is what the book tends to favor for these aldol reactions. Disadvantage is that sodium hydroxide is not soluble in organic solvents, so you have to wait a lot longer for things to dissolve. So you've got to practice working problems in the back of the chapter so that you're good enough that you're not spending 10 minutes trying to figure out these disconnections. Right? And you'll quickly become very good at that by working some problems. But unless you do that, you're not going to become good at seeing aldol reactions unless you've practiced bunches of problems. Okay, so I've got a mixture of intermolecular, intramolecular, additions and condensation reactions on this slide, and you need to know how to master. You need to master all of those types. Now I want to talk, sometimes you don't want two of the same molecules joining together. Sometimes you want to join two different pieces together using an aldol reaction, like that citrate example that I showed you. And we refer to these as crossed aldol reactions, when one molecule forms the enolate and then it adds to a carbonyl on a completely different type of molecule. That's called a crossed aldol reaction. So let's go ahead and talk about what is a recipe for a useful crossed aldol reaction that gives good yields. A useful crossed aldol reaction that is efficient. So here I've drawn out an example of a useful crossed aldol reaction that is likely to be efficient. In fact, I know this one is efficient. So one of the key parts of this recipe for an efficient crossed aldol reaction is that one of the components should be an aldehyde without alpha CHs. And if you don't have that, you're going to have a hard time designing an efficient crossed aldol reaction. If you don't do that, you're going to end up with both molecules are forming enolates and both molecules are attacking the other carbonyl, and it will be a horrendous mixture of lots of things. So in this case, you can see down here, one of these components has an alpha carbon, and it has alpha CHs on there. So certainly that one can form an enolate. You can also attack the carbonyl on that one as well. So what's its role going to be? Let me come over here and look at this other molecule, and I'll notice there isn't even an alpha carbon on this side. It's an aldehyde, so there's no alpha carbon here, right? So if there's no alpha carbon, there's no need to discuss whether there's alpha H's on the alpha carbon, because there isn't even an alpha carbon on that side. When I come over to this other side over here, well, that one doesn't have any CHs. So no alpha H's. So this aldehyde, it's called pivylaldehyde, can't actually form any kind of an enolate. There will be one and only one enolate species in this solution. You'll generate tiny amounts of the enolate from the ketone in this case. And notice how cleverly this recipe has been designed. You'll notice over on this side, just to make sure it's a clean reaction, they chose a substrate here that has no alpha CHs, no alpha H's on this other side. So you can get one and only one enolate species floating around in this reaction mixture. That's how you're going to get a recipe for a clean crossed aldol reaction. Because if I had alpha H's, or an alpha carbon with alpha H's on the other side of this ketone over here, well, then I'd have to worry about two different enolates floating around, doing two different things, making two different sets of products, and that just sounds like a nightmare. So let's go ahead and walk through what's going to happen here. So the arrow pushing reaction is going to look like this, right? You'll come along with a base. I'm just going to symbolize that base with the letter B. I don't have a lot of room here. Right? The conditions are basic. If the conditions were acidic, I would write the symbol A-. So I'll go ahead and do the arrow pushing. I'll go ahead and leave the electrons over here on the alpha carbon. Let me try to do that more precisely. You could push the electrons up to the carbonyl. That would give you a resonance structure, which is fine, but I just want us to be able to see that carbanion so that we're ready to think about bond formation. I'll use the symbol AR here for our aryl group because I don't have room to draw that in. I assume everybody knows that's not argon because you can't form bonds to argon. It's a widely used symbol for aryl group, Ar. Okay, so there's our enolate. And now what happens in this reaction is that you do an addition to this aldehyde. So we'll go ahead and add to the aldehyde, form a carbon-carbon bond. That's exciting, right? So you know adding Grignard reagents to carbonyls, you know adding to make carbon-carbon bonds, acetylide anions to carbonyls, alkylithium reagents to carbonyls, and so now here's another powerful carbon-carbon bond forming process. And this is the one that nature uses. Nature doesn't use alkylithiums or Grignard reagents. It manages to do everything with this powerful carbon-carbon bond forming process, the aldol reaction. Now I'm not going to show you the rest of the mechanism here, but you can see, right, that this is going to protonate. Whoops, let me take one of these arrows out. There we go. This is going to protonate under the conditions of the reaction and give you the aldol addition product. And because you're heating this is going to go all the way and give you, I'll just draw these two steps here. So under the conditions of the reaction, this gets protonated. Don't draw HA, draw BH as your, because the conditions are basic. So use HB as your acid. Use B for, if the conditions are basic, use B, symbol B for your base. Use HB as your acid species. Don't write HA, please. I wouldn't count off, but it doesn't make sense to draw acidic species under basic conditions. All right, so that's a crossed aldol reaction. It's just like a regular aldol, except the two pieces are the same. So, and it works because you don't have to worry about this enolate over here, or sorry, you don't have to worry about this aldehyde over here forming a second enolate that's floating around. So what are the common aldehydes that don't have alpha CHs? That don't have CHs that can be deprotonated? I'm going to draw the most common partners. There's 4 of them for crossed aldol reactions. I'm not sure if they're still doing this in the Chem 51LC lab, but they used to have an experiment where you took like 4 different types of ketones and added, 4 different types of aldehydes, and every group was making a different aldol condensation product out of that through crossed aldol reactions. And let me show you the most common aldehydes for doing crossed aldol reactions. So here's one of them. Here's one of the common ones. Right? You wouldn't want to pick this one over here because look, that's not a good aldehyde for a crossed aldol reaction because that's going to be forming enolates just like the other component. So here's some good examples of aldehydes that are good for crossed aldol. Here's formaldehyde. It's just an insanely reactive carbonyl compound. And it doesn't even have any alpha carbons. So you don't have to worry about formaldehyde forming an enolate. There's no chance. It doesn't have an alpha carbon. How could it form an enolate? Here's another one that it's the same one I just showed you. It's called pivylaldehyde. Organic chemists love this. A little bit hindered, but it makes the NMR easy to interpret. So pivylaldehyde has no alpha CHs. I mean, one side doesn't have an alpha carbon. The other side has methyl groups all over the alpha carbon. So another common substrate for crossed aldol reactions are benzaldehyde derivatives, where on one side there's an H, so there's no alpha carbon, and on the other side there's some sort of a substituted benzene ring, right? You can have chlorine groups on here. I'll just put this. I'll put X. That'll be a substituent. It could be ortho, meta, para, doesn't matter, right? Just any sort of an aryl ring attached to an aldehyde group. That's great. There's no alpha H's on a benzaldehyde derivative. And then the last one is a little bit weird because there is an alpha hydrogen. It just can't be easily deprotonated. I don't want to run out of room here because it's slightly elongated. But this other one would be just an enal, a double bond conjugated to an aldehyde. Right? And this R group could be whatever you want there. And the idea is that it's not easy to deprotonate this. You would end up with this weird cumulene system with 3 double bonds all attached in a row. It'll look weird to you if you try to deprotonate that and draw a resonance structure. And the most common ones are when this R group here is a phenyl group. That's called cinnamaldehyde. That's what gives cinnamon its flavor. So it's a readily available chemical compound. All right, so those are the common players for crossed aldol reactions, and chemists love to use these crossed aldol reactions to make complex molecules, and that's why you'll be doing that kind of thing in the laboratory. Okay, so let's talk about the other component in a crossed aldol reaction, because you have to be pretty careful here with the recipe. Here's an example where we've correctly chosen the aldehyde, but what about the ketone part? Usually it's a ketone. In theory, it could be an aldehyde as your other component. So you can see here we've carefully chosen a component over here that has the aldehyde component has no alpha CHs. No alpha CHs in there. So there's no way that this aldehyde, benzaldehyde, can form an enolate. There's only going to be one thing forming an enolate in here, and that's going to be, this one right here. And let's go ahead and talk about that. Why should that work? So in other words, when we run this reaction, we're going to get one and only one mixed product out of mixed cross-aldol reaction product out of this. And that's where the enolate from the ketone does an aldol condensation. I'll write sodium hydroxide. And because there is linear conjugation here in the product, you can see that linear conjugation going from here through to the carbonyl, right? That tells me I don't need to heat it. But I'll write heat anyways, just because if I'm trying to make something do an aldol condensation and do the elimination, I would add heat. Heat favors elimination over substitution processes. It's just a general recipe for getting elimination to go. So notice what's not happening here. That when you're forming this enolate from the ketone, one of the things that is not happening right here is you are not ending up with this problem. You don't end up with the problem where this enolate is coming back in and attacking another molecule of the ketone. Now, if you didn't add any aldehyde, that would be a problem. But why is this not a problem? Right? Why is this not occurring under the conditions of the reaction? Because it certainly could occur. We told you that you could do aldol, or at least the book tells you you could do aldol reactions with ketones. But the issue is not that that's impossible for it to occur. The issue here is that this aldol reaction with an aldehyde is faster. So aldehydes are about, if everything else is equal, an aldehyde is about 1,000 times, an aldehyde carbonyl is about 1,000 times faster. I'll just write 1,000 times faster than addition to a ketone carbonyl. Aldehyde carbonyls are about 1,000 times more reactive than a ketone carbonyl. Now, if you threw in a Grignard reagent, which is just so crazy reactive, you might not get a lot of selectivity. But an enolate is not as nucleophilic as a Grignard reagent or an alkylithium, and so you can get very good selectivity, right? You don't see the ketone enolate attacking the ketone carbonyl. So aldehydes are reactive. That's why these crossed aldol reactions between ketones and aldehydes that don't have CHs are a good recipe. Now, we talked about in the last chapter carbonyl compounds that have two anion stabilizing groups, two carbonyls, one ketone and one ester, two ketones, one ester and another ester, and they really make these CHs here super acidic, right? These CHs are just so acidic right here. Remember, those are more acidic than water. If I make the carbanion by deprotonating and put in water, the carbanion will just sit there and it can't get protonated by water. It's amazing that could still be nucleophilic when it's so easy to deprotonate and make the carbanion. How could that be nucleophilic? But it is. Enolates are nucleophilic. And so we can use these same types of stabilized, highly stabilized enolates that come from 1,3-dicarbonyl compounds. So again, why is it called 1,3-dicarbonyl? Well, you count the numbering here, 1, 2, 3. That's a 1,3-dicarbonyl compound. The numerical relationship between those is 1 at 1, the 1, 3 positions. And you'd get a similar reaction, right? It's not different. All right, let me just say, you'd get a similar thing if you used, for example, also an ester on one side and a cyano group on the other side. Cyano groups can stabilize carbanions kind of the same way as carbonyls. Or you could have a cyano group on both sides, or you could have ketone on one side, ester on the other side, same idea. So sodium ethoxide, it would be a great base to use in order to make enolate and then do what is essentially a crossed aldol condensation. Well, we have a special name for this. I'm taking liberties with the name here. This name is generally associated with something else, but when I showed you that slide with the citric acid cycle, I'm pretty sure they used this phrase on there, Novanagle. This is called a Novanagle condensation. So you're condensing, it's a crossed aldol, but you're doing it with one of these highly stabilized enolates. Oh, sorry, that was the Claisen condensation they were referring to. Sorry, but this is a Novanagle condensation. You don't have to know that, but if you see it somewhere in the book, they're referring to this aldol condensation, crossed aldol with highly stabilized enolates. So any other thing that has these two anion stabilizing groups could also engage in this type of crossed aldol reaction. Now, we have to be super careful with our base here, right? And we're going to talk about this more shortly, though. But let's take a look at this. What would happen if I use sodium hydroxide here? That is right. It is true that sodium hydroxide could deprotonate between those two carbonyl groups. The problem with sodium hydroxide is it is very fast to hydrolyze esters. You put sodium hydroxide in there, you're simply going to hydrolyze the esters. You won't get any of the desired Novanagle product, the aldol condensation type product. So I'll just put a big cross through this. Don't do this. Right? Don't put sodium hydroxide in there because it hydrolyzes esters very efficiently. Doesn't require heating, right? So, boy, you've got to be very careful about which base you choose for these types of reactions, these types of Novanagle condensation reactions. Now, I want to show you a modern version of the aldol reaction that is much more common than everything I just showed you, because this is the way we do modern organic synthesis. You know, when we do modern organic synthesis, we don't just throw sodium hydroxide in with carbonyl compounds. That is so archaic. Nowadays, when we want to make an enolate, we want to make 100% enolate and then throw in any aldehyde we want. And so the way to do that is the same way I showed you in the last chapter. The way to make 100% enolate is to use LDA in THF at -78. This makes 100% yield of the enolate by deprotonating, right? You get 100% yield of this, and as long as you keep it cold, you can go off to lunch. Don't leave for very long. Go do some other stuff, read the news, chat with your friends, and then come back and dump in some aldehyde into that reaction, right? It's so much more controlled when you do this kind of a directed, they call it a directed aldol reaction in this part of the chapter, where you're using LDA to make one specific enolate. And you can see what's happening here is because you're using LDA is selective for the least hindered side of a ketone. Right? The ketone has about equal acidity on both sides, but you don't see any deprotonation here. Right? Not here, because LDA is choosy. That's what the two isopropyl groups on LDA are for. They make it very, very, very choosy. And it will 100% select the proton on the least hindered side to give you 100% of one enolate. And you can't get that kind of selectivity using sodium alkoxide or sodium hydroxide. So now if you come along and you add in an aldehyde, in this case I've drawn it adding to an aldehyde that has an ethyl group. That's 3 carbons, that we would call that propion aldehyde. Propanal maybe would be the IUPAC name. And so now this is a directed aldol reaction. In 100% yield, you make the enolate, then you come along and you squirt in some aldehyde if it's a liquid, and that leads to formation of a new carbon-carbon bond. And you'll notice, though, that we have to come along here and work this up. We have to add water to this to protonate that O-. So the product here is an O-. And so if we don't add that water molecule, the water in our workup, we'd be stuck here at this O- stage. So, I'll go ahead and draw the mechanism. It's not an interesting mechanism. B, right, HB. I was about to write an A there. We spent so much time doing acid chemistry in this class. So, and that would just simply protonate that in the aqueous workup. So that's a directed aldol reaction. It is much more controlled. You get to decide when, well, with LDA, it will be very choosy and will deprotonate on only one side of an unsymmetrical ketone. And then you can come along and add any aldehyde that you want there as your product. So this would be a directed aldol reaction. And this is the common way to do aldol chemistry. So how is this useful? I mean, you can see that when you've got this kind of control, you can make very thoughtful decisions about the kinds of molecules that you're constructing. So when I look at this molecule right here, man, my thought is enolate, enolate, enolate. This is like an extravaganza of enolates here. How would you do that? Well, here's what you would do. You want to make an enolate? Don't go get sodium hydroxide. You come along and you use LDA and THF at minus 78. Let's draw that out. Step 1. I want to make an enolate. LDA, THF, and minus 78 degrees Celsius. And you might think, oh, I don't have room to write that in there. Sure you do. Look, I fit it in there. I'm on this cramped little iPad screen in that little box. Now, step 2, we got to figure out, once we make an enolate on one side or the other, it's symmetrical, so it doesn't matter which side. So let's suppose that we make an enolate over on this side first. You know, we get to choose which of these two bonds we want to add first. You know, do we want to make this bond over here first or this bond over here? I actually don't want to have a hydroxy group dangling around when I add LDA again. Right? You can't do that. You can't have this hydroxy group and then come along with LDA and deprotonate the other side. We have a trick for that. We use silo-protecting groups, and then we can make LDA deprotonate the other side. But so in order to avoid that, I'm going to add the aldol group first because it has no hydrogens, no acidic H's on it. Step 2. I'm going to add allyl bromide. I'm going to make absolutely sure I have the correct carbon count. Right? See how careful I am? Let me count it up to make sure I didn't make a mistake. 1, 2, 3. 1, 2, whoops, 3. Okay, didn't make a mistake. You know, over and over again, I've seen students make mistakes missing a CH2 group or something. And I know you might be thinking, oh, I'd never make that mistake. Yeah, you will. It'll be an exam. You'll be panicked. There's 2 minutes left. You got to write down the thing quickly. And I'm going to see people making a mistake where they forget to draw this carbon atom here, the CH2 group right there. So try to be careful with that. So this reaction would put an allyl group on one side. Doesn't matter, it's symmetrical, so I'll try to orient it. Notice how I'm going to draw it the same orientation that the product is drawn. You could put that allyl group flipped around any way you want, but why not try to make it look like the product? That'll help reduce confusion. It's just a simple trick when you're trying to do mechanisms or when you're trying to work out total synthesis, is draw the intermediates in the same orientation. Or redraw the starting material in the same orientation as the product. And that'll help you to see what you need to do as far as what reactions you need or what mechanistic steps you need. So now what do I do? Now I've got to add this other piece on the left-hand side. Well, I'm going to make an enolate. And I can only do this selectively on the least hindered side. But that's good, because that's exactly what I want. LDA, THF, minus 78 degrees Celsius. There we go. That's going to make an enolate over on this other side. So now I'm going to deprotonate on the other side, completely selectively, and now I'm ready for carbon-carbon bond formation. I could add another allyl group, do SN2 chemistry with methyl iodide or allyl bromide or a benzylic bromide of any kind. But here we're doing an aldol reaction, because that's the theme of this chapter, is aldol reactions. And so the aldehyde we would add in would be benzaldehyde. There we go. And remember, for these directed aldol reactions, we have to work those up with an aqueous workup. Step 3. And once you've done this, right, as soon as I see this molecule, I want to do more chemistry with that. You know so many reactions right now that you could apply to this for multi-step synthesis. You could oxidize this to a carbonyl. You could protect that OH group if you wanted. as a siloprotecting group, and then you could do Grignard additions to this carbonyl. You could do Wittig reactions to the carbonyl if you protect this OH group as a siloprotecting group. You could make imines. You could, in theory, make enamines. Over here on this other end of the molecule, you could add HBr across that double bond with or without peroxides. You could convert this into a acetal. Again, you got to be careful about this OH group for some of these reactions. Do hydroboration oxidation. There's a whole bunch of reactions you could do once you start forming carbon-carbon bonds and making things bigger and longer. And so this is what makes organic chemistry very powerful, but it also makes it a challenge for you when you're learning these tools. There's so many vast numbers of variations on the synthetic sequences that you can put together. That you really have to practice this to see these reactions work in various contexts. All right, so I kind of hinted at this before, but it is certainly possible to do intramolecular aldol condensation reactions. And this is extremely common. You know, again, when you look in nature, nature loves to make cyclic compounds that are 5- and 6-membered rings. Nature also makes 3- and 4-membered rings in plants and natural molecules, but 5- and 6-membered rings are so favorable. So I expect you to know how to work out aldol reactions that have occurred intramolecularly. So let's go ahead and take a look at this. The key is that really aldol reactions are only going to be efficient for 5- and 6-membered rings. 4-membered rings are too strained. You're not going to be able to make a 4-membered ring through an aldol reaction. 7-membered rings, maybe, but they're just not as favorable. If you have a choice, make a 5- and a 6-membered ring. When I see this product over here, this is called an indenone, I can see that there's a bond there that must have come from an aldol reaction. It's screaming at me that it came from an aldol reaction. And I've done enough aldol problems, working problems in the backs of chapters, that I can tell I must have made an enolate here and then added that to a carbonyl over here. And you could use any kind of alkoxide base, sodium hydroxide, sodium methoxide, sodium, right? We don't have any esters that we have to worry about deprotonating here. And you don't need to say heat here because there is this kind of linear conjugation starting from the carbonyl back to the benzene ring. That elimination, the E1CB elimination, will be spontaneous, but I'll write heat there anyways, just remember that. Now, this 5- and 6-membered ring issue is important. So when we look at a substrate that looks like this, now we have to worry about over here with these two carbonyl groups. There's a ketone on the top and a ketone on the bottom. Actually, this molecule is symmetrical. If you look very closely, there's symmetry starting right here, and it's the same on both sides of that. I just oriented it so it doesn't look symmetrical. But if you tried to do an intramolecular aldol reaction on this, you have to worry about the fact that, well, I can make enolates on this side if I'm using sodium methoxide, or I can make enolates on this side if I'm using sodium methoxide. So, and in fact, methoxide or ethoxide or hydroxide is going to be forming both of those enolates in solution. Tiny amounts of those enolates. 1% of this will exist as the enolate on both sides. And so how do you know which of those two enolates would be forming bonds through an aldol reaction? And here's how, right? There's certainly nothing that stops you from deprotonating over here on this side. There's H's on this side that can easily be deprotonated by a base like hydroxide or ethoxide anion. And so once you form that enolate, it turns out that you don't have to worry about this 4-membered ring formation because it's too strained. So that's not going to happen at an appreciable rate or with an appreciable equilibrium constant. So that means it's going to be the other side that's going to lead to the aldol reaction. So let me go ahead and draw what would happen if I deprotonated on the other side. If I deprotonated on the other side of the ketone, and I'm going to be very careful. You guys probably aren't as good at drawing these systems here. I'm just making sure, what am I doing when I draw this out? You can't tell what I'm doing here, but I'm making darn sure that I've drawn 3 CH2 groups in a row. 3 CH2 groups in a row, 3 CH2 groups in a row. And you're likely to make a mistake if you're not careful about that. Okay, so now I've got my system set up and I'm ready to think about, okay, here's the alternative. Could this do an aldol reaction? And if I count the carbon atoms between here and that carbonyl, 1, 2, 3, 4, 5, 6-membered ring transition state. That is awesome. That's going to be a great aldol reaction, right? If you're attacking something 5 or 6 atoms away and doing an aldol reaction, that is going to be a sweet setup. Now I'm going to go right all the way to the final product here, right? And how do I know that's the right structure and I didn't blow it some way? Well, I'm going to come back here and I'm going to check. I've got, right, I'm checking here. I've got 1, 2, 3 CH2 groups in my ring. Notice how carefully I was checking? I'm not too busy. 1, 2, 3 CH2 groups, just like the 1, 2, 3 CH2 groups over here. Just like methylene group number 3, methylene group number 4, methylene group number 5. And then there's a carbon over here that has no H's on it. You have to be that careful when you draw out these aldol products because it's so easy to make a mistake when you draw the structures out. And the way you're going to get practice with that is to go to the back of the chapter and work a bunch of problems. And then check your answer. In the answer key, I posted solutions to all the problems in the backs of the chapters for our course in our Canvas files. So I urge you to try to work through the problems and get practice with aldol condensations, aldol additions, directed aldol reactions. Now, it's kind of hard to think about that right now because I know you're getting ready for our exam on Monday. So you just have to well, you have to keep this stuff in mind and come back to it after the exam. So, okay, work every problem you can get. Come to our study halls that we have. Mine is tomorrow morning and another one on Friday morning. So, love to see you there because you can just hang out and study. And I'm there to answer questions, or you can listen to other people's questions. We sure do appreciate it when you come and take advantage of us. Use us.